The next speaker will be Jörg Schröder from Bio University in Xi'an. He will be talking about the sum integrals, from sum integrals to continuum integrals and back.
Okay, thank you, Goratz. I go to full screen. You see the presentation, right?
Yes, we see.
Okay, perfect. So I'd like to take you on a brief ride, given the conference format, on a very simple but most enjoyable project that I've been working on in the last year or so with Andrei Davidichev, who visited Chile, and earlier than that with two of my former PhD students, Johan Gishoyo and Jan Möller. I say a simple project because those who know me from the yearly AFUNALUE talks have probably spotted a pattern. Every other year I give a talk on collider physics, namely very high perturbative expansions in quantum field theory. And recently we've been obsessed about some kind of 5-loop renormalization of QCD and the Higgs production rates associated to the gluon-gluon collisions. And the year which is the AFUNALUE conference of this year, I usually then talk about some other hobby of mine, which is concerned with thermal field theory. We've already seen a couple of those topics briefly today in Marcelo's and Christian's talk. So now going to thermal field theory, what strikes me there is coming a bit from the continuum collider physics community. The methods, computational methods, there are not very much developed, by far not as much developed as they are in the collider physics community. So there's a huge potential for making advances in evaluating with precision some observables. In this talk, I try to, given the time allocated for it, I try to spend about half of it with setting the stage with the motivation, and then spare you most of the technical details before I conclude. So just to give you an overview of what one could be motivated by to do finite temperature field theory. It's by now a fairly mature subject, I would say, and I measure maturity by the number of textbooks you can access. And I shall maybe advertise a kind of recent textbook by two of my collaborators, Nikolain and Alexei Vorovin, here. But first and foremost of all, the relevance of finite field theory comes from its applications, right? It's relevant in cosmology, where one is then mostly concerned with the weak interactions, weak interacting part of the standard model, and QCD processes are more or less just a background. Yeah. In cosmology, one might want to study the early universe, the expansion rates, the equilibration, the reheating temperature. What is the maximum temperature reached in reheating? Dark matter searches. What are the relic densities of dark matter particles proposed that couple in extensions of the standard model? But also finite temperature field theory is very relevant in heavy ion collisions, so in the laboratory, in earthly laboratories. And there it's mainly QCD. We've already heard in Marcelo's and Christian's talk some aspects today. There one is concerned with a rapidly exploding fireball, right? Temperatures are of the order of 100 MeV, and these are typical QCD temperatures. So their QCD will be playing a huge role. And then one might ask for particle yields, jet quenching phenomena, the hydrodynamics of the expanding plasma, etc. So I will go to a very simple setting. I will be focusing on explaining something connected to equilibrium thermodynamics. There one can use the imaginary time formalism, and I'll briefly here explain what that means. Well, as the name says, it means placing the time for an imaginary parameter tau. But what you're really doing in imaginary in equilibrium thermodynamics, if you might remember your your classes of thermodynamics or statistical physics, you're working in some ensembles where you really want to evaluate things like the partition function. These are traces of operators, right? Traces in equilibrium, and these traces, well, they are cyclic. Traces, as we know, are cyclic objects. So if you do the path integral quantization, the fields become periodic, and this means that in the path integral quantization, what you get is that one of the dimensions, namely the temporal dimension, compactifies. Right? It's not an integral from over the whole real line anymore, but it's a compact integral in a circle, one could say, which is over a finite interval. And this is the main difference. So the d-dimensional space stays intact, and the temporal dimension is shifted to this imaginary time, which is compactified. And then all of a sudden one realizes, well, once you have a compact dimension, it's the usual Kaluza-Klein idea, for example, in momentum space, the energies, they are discrete. Right? So what one has to do if one now does any computations in this path integral formalism for equilibrium fields in thermodynamics, one has to sum over the energies and integrate over the momentum. And this is hell difficult. Integrals, continuum integrals are kind of nice. There's tons of tricks from continuum collider physics, lot of newly developed integral tricks how to solve continuum integrals. Some are hell. The mathematicians don't know a lot about classification of sums. But anyways, one gets these sums, and then the propagators always have a discrete part and the continuum part, so one has to do sums and integrals. So the upshot of all this motivation is we have to shift our attention from computing integrals to computing sum integrals. Okay, a very clean subproblem within these sum integrals are vacuum type sum integrals. So I'm taking away all the external momenta of scattering processes. One can imagine a Taylor expansion or some kind of mass expansions, etc. And why this is relevant in thermodynamics is because we want to evaluate something like the pressure of an exploding fireball, of the exploding early universe, etc. That's connected to the negative free energy, right? So these are the corresponding vacuum diagrams. One really computes the partition function of the standard model or QCD. That's connected to expansion rates, equation of state, etc. And I think the most clean problem within this subproblem is to consider only bosonic problems. So I'm thinking of a soup of gluons here. And these are vacuum type sum integrals, which only have bosonic degrees of freedom. Where the state of the art is actually, to me, is surprisingly low. At 1 and 2 loop, one is kind of okay. One can compute many processes. From 3 loop on, that's the frontier. So we've been working on that for a while. There's isolated 4 loop cases which have been solved in this setting, but that's too hard for the moment. So let's go to the most simple setup here. I will first briefly explain how the state of art looks at, or how the matter looks at 1 loop. If you want to compute a 1 loop vacuum integral, here's one typical one. At 0 temperature is very simple. You can just take the integral, you get a gamma function. This is well known. If you're now doing the sum integral, finite temperatures, you have to do a sum over these finite discrete modes, Matsubara modes. Here's a sum integral. And what you're getting is a sum, in a sense, over these continuum integrals where you sum over their masses. The mass is now some kind of discrete parameter. And if you're summing over mass here, it's so simple, then you're getting zeta function. Here's the zeta function, and the rest is as at 0 temperature. So you're getting zetas, typically, when you do the sums. Fine. Why is this relevant? Well, just think of black body radiation, for example, right? The well-known pi squared over 90, the free energy of 1 degree of freedom. Like in QED, it would put 2 degrees of freedom. You want to play with the expansion rate of the universe at a couple of MeV or so. Gets this p squared over 90 exactly from these types of integrals. Okay, so obvious next step, right? Let's go to 2 loop. Let's see what happens. There's a couple of worked out examples in the literature. And in general, what people have observed is that there is no really genuine two-loop sum integrals. One could always write it as a factorized, as a product, which factorizes into two one-loop parts. And then the question is, obviously, is this a theorem? And the answer, and I will show you in the next couple of slides why this is, so is a resounding yes. This is a theorem which one can rigorously show, at least for the class of integrals that I'm looking at, the bosonic ones. Why is it good to have some kind of factorization? Well, usually when you compute higher orders, you want to have analytic results, right? And not just numerical approximation of some kind of expansions around the dimension of interest. So the setup is the following. I would like to look at the simplest two-loop integral in d dimensions. So it's given here. It's just a double integral over 3 propagators. That's a vacuum integral at 2 loops at 0 temperature. And then I would like to sum over it, sum over the masses that are here. So I do this double sum, and then I get the double vacuum sum integral. I call this L in my talk, and B is some of the 0 temperature correspondence of that. So what I want to do is do the double sum, like at 1 loop, over these 0 temperature integrals. Now the 0 temperature integrals, and that's why I work with Andre, is known since a long time, since almost 30 years. Unfortunately, it's an upper function, and that's extremely nasty to sum over. We can't do. So this double sum over upper we can't do. However, one can do much better in this respect, because the masses are related. As you can see, the 3 masses have a linear relation, finite temperature field 3, and the relation is this one. One mass is always the sum of 2 others. We noted that that exactly corresponds to the 0 of the Shalin function, which one knows well from relativistic kinematics, right, in collider physics. So exactly when this linear relation is fulfilled, it means Shalin function vanishes, which leads to much simpler relations between integrals. So we've been playing with integration by parts, IBP, and dimensional relations. Here are some of them for the 0 temperature integral. I won't go into details, like I said, I won't show many technicalities. But these relations, they assert us that the 0 temperature integrals are polynomial in the masses. And that is super important information for us at finite temperature, because we want to sum over the masses, right? So if we know the polynomial, we can try to sum over this polynomial. One can actually prove an explicit form for this 0 temperature integral. Here it is, and here are the 2 masses. There are some permutations there. And what's left over is now to do the sum to go back to finite temperature. Okay, so going back to finite temperature, one has to do a double sum. This can be decomposed in a couple of different regions. And so one wants to do double sums over some positive regions of the 0 temperature integral. And actually that can be done. And then there's a long proof and beautiful mathematics and some conjectures which then later have been proven recursively, etc. The details we put in a forthcoming paper, but we can show that this really, I mean, by definition, double sums are multiple zeta values, right? But they all cancel, and we are left with only single zeta values, namely with products that we can rewrite in terms of this one loop sum integrals. So in the end, one gets a closed exact formula for 2 loop sum integrals in terms of a factorized sum of 1 loop integrals. Okay, and once one has that, so the question is obviously, so what have we gained? Well, we have this exact evaluation now of a new type of 0 temperature 2 loop integrals, which actually is related to a 1 loop 3-point function with collinear momenta, which are relevant in phase-space distributions. But what we really want to do for the finite temperature case is generalize this whole setup, right? As we've seen earlier in talks by Christian and Marcelo, maybe also fermionic degrees of freedom are very important in QCD. So the next obvious steps would be now take our 2 loop development, include fermion masses, chemical potentials, maybe even magnetic fields. And then obviously, that's some of my interest, my particular hobby, generalize the whole thing to higher loops where we have not yet done steps, but just checked some cases. Okay, That said, I think this whole program of trying to incorporate methods from zero temperature collider physics into finer temperature field theory seems to prove kind of fruitful, given also new results at zero temperature in zero temperature physics, and trying to get to increase some of the frontier of precision in finer temperature field theory. And with this, I close the talk. Thank you.
Okay, thank you, Jörg, for the nice presentation. Are there any questions?
Yes, I have a question, Jörg.
Yeah.
My question refers to convergence of the expansion. How do you control that?
That's a fantastic question. I haven't shown you any expansion in this talk of any observable, but the question is relevant because as you might know, in QCD, the bosonic part of QCD, the gluons, really give an infrared problem, which can be cured within effective field theory. And for evaluating the coefficients of these effective field theories with precision, so getting around this infrared problem, one does need, I mean, things start to get interesting exactly here at this two-loop level. Where one really wants to go, concerning your question with convergence, is the four-loop level, counted in terms of some integrals, not yet going to effective theories. And so these methods that we are trying to develop here, they're aiming at getting some leading order predictions or postdictions for things like entropy, pressure, free energy, or full QCD, where the fermionic sector is just converging like a charm because of the masses. But the gluonic sector with all this infrared problem, they need some higher terms to have a chance to be convergent.
Thank you.
Any other questions? Okay, I have a short naive question for 3-loop or 4-loop expressions. Are there some numerical results, evaluations, or in this sums, is there any problem of convergence at higher loop?
Oh yeah, for sure. For sure, the first tries that one always aims at are some kind of ballpark numerical results. But as you quickly saw, these sums are typically over multiple zeta functions, or in the continuum case, polylogarithms. They converge extremely slowly. So even to get these infinite sums under control, and now you're talking about 3-loop, a triple sum, numerical under control, is absolutely hopeless. And that's why one really needs analytic methods here to get any progress, to get any precision. Not even the order of magnitude one can fix in a triple sum or quadruple sum of this type.